Good morning or good day, and welcome to the inaugural Hydrology Section's Early Career Awardee webinar series that we've been running all this month. I'm Scott Tyler. I'm the president this year and last year of the Hydrology Section. It's my pleasure to welcome all of you to today's webinar. The Early Careers Awards are given to up to 3 scientists, young scientists in the section, 10 years since their PhD. Successful nominees are scientists who've demonstrated outstanding contributions to hydrologic sciences, education, or societal impacts, and also show exceptional promise for continued contributions to hydrology throughout their career. This year, we have 2 amazing researchers who've been sharing their stories with you, Veronica Morales and Simone Fatichi. And today we have our final Early Career Award winner, Niko Wanders from Utrecht University. Sorry, I just got some new screens on my computer and I'm trying to figure out how to make them work. Just a few logistics for today's series. We're going to be recording the webinar, so it will be recorded and it will be up on the hydrology website at HEU in a few days. Last week's seminar is up there as well under our lectures and awards. So if you missed it last week, if you missed Simone or Veronica, please take a look. You can grab those very quickly. If for some reason we have some kind of a technical issue during the presentation, we'll try to bring it back. If we fail, we will record the video offline and then make it available to all of you. As we go through, as Niko is giving his lecture, please type your questions into the question box. If you prefer not to have your name read, just make a note that you prefer to be anonymous and just keep putting those questions in. You can put the questions in as we are going through the lecture. They won't disrupt the flow of the lecture at all because the speaker doesn't necessarily see them. So I'll read as many questions as we have time. And I think that's enough from me. You'll see me at the end. We have a few announcements for the fall meeting, and I will catch you at the end of the seminar. It's now my pleasure to introduce Dr. Reid Maxwell from Princeton University to introduce our awardee winner this week, Dr. Niko Wanders. Reid?
Hi, thanks so much, Scott. It's with really great pleasure that I introduce Niko, Dr. Niko Wanders, who's assistant professor in geosciences at Utrecht University. Everybody who's Dutch just cringed. As one of the 2020 AGU Early Career, Hydrologic Sciences Early Career Award recipients, and our 3rd speaker in this amazing seminar series today. Just a quick introduction. Dr. Wanders has made really impressive contributions in 4 areas: understanding drought and its feedback on human water use, hydrologic modeling and forecasting, hydrologic impacts of climate change, and hydrologic remote sensing. Wanders' research is at the forefront of understanding the large-scale relationships between hydrologic extremes, climate change, and human water use, which is exactly what you're going to hear about today. Dr. Wanders has won numerous awards. However, I'm not going to spoil the citation. You're going to have to tune in during the AGU award ceremony to hear more. For now, let's all give a virtual round of applause and welcome Dr. Wanders' lecture on frontiers in hydroclimate change.
Thanks, Reid. Thanks, and welcome to you all to my lecture, Frontiers in Hydroclimatic Change. I want to start by thanking some people who have been very important for my career. Of course, my nominator, Dr. Reid Maxwell, who just gave me a very nice citation. The letter writers, Dennis Lettermeyer, Martin Clark, and Lennart Alexen, who supported the nomination. And of course, some mentors I've had along the way. Henny van Laane from Wageningen University, bottom left. Eric Wood, Princeton University. Mark Bierkens, the top right, who's now also one of my mentors here in Utrecht, and Stephen de Jong, who's in the center of the picture, who actually gave me a PhD in, although we're talking today about droughts, where he gave me a PhD in floods. So, and of course, I want to congratulate Veronica and Simone. I also like to thank my family, who's not only supported the work I do, but also deal with my daily fascination for hydrology and drought. And I think one of the signs how we can see this is by the disturbing amount of pictures with water-related items I have for my holiday. So I also would like to thank them and for taking me outside as well for my parents. So you come from the Netherlands. Why do you study drought? I mean, it's the country known for floods. Actually, we had a couple of big droughts running 2018, 19, and 20. Here I have an animation from Philip Krijbrink, who's a postdoc here in Utrecht, showing the impacts of droughts. And it's actually, what fascinates me here is that it's kind of a large-scale phenomenon. It's not like one location. You see in northern France, the UK, but even the Netherlands, you see yellow vegetation popping up. So even a country like the Netherlands is hit. And some of the impacts that we have, for example, or that here globally have, is basically loss in crop yield, problems with drinking water supply, energy production, of course, shipping. When there's no water, shipping is going to be very difficult. Forest fires, damage to nature or biodiversity. A very Dutch one is soil subsidence. You see the girl on the bottom right, her front step used to be like 0.5 meter higher. For her, this is a significant impact. As you can see, she has to carry her very Dutch bike now inside. Then there's a conflict, one area I've recently worked into, and we'll show you some preliminary results on that. And of course, the economic impact of droughts. There's 3 types: meteorological drought, basically caused by precipitation and evaporation; agricultural drought, soil moisture; and then hydrological drought. That's the one I focused on most frequently, impacting components like groundwater, river discharge, and reservoirs. And drought is not something just of the last 20 years. Actually, I have here this paper by Evans et al. From Science, and they actually used lake deposits to indicate, for example, how the Maya civilization was affected by droughts. And whether or not it caused their collapse, that's still up for debate. But at least you see that droughts have already quite a historic impact. But for this lecture, we'll focus more on the current and the future. But I wanted to show that it's not just something that is happening now thanks to climate change. I want to start with this graph by Justin Sheffield from Nature in 2012. Actually, before I got to Princeton, they published this, and it shows very nicely the development of global drought around the world. And he showed, together with Eric, that it's important to also look at the impact of temperature when you're doing your evaporation calculations. So we have this problem with droughts that we try to relate them to the past, but we also have an ongoing trend on top of that. So you see here on the top, the PDSI is the Palmer Drought Severity Index, a frequently used drought indicator. 0 is average, and everything in the negative is a drought condition. You see here the global average, and you see without a temperature correction, that's the blue line, you see severe droughts everywhere past 2000 on average on the globe. But if you take into account temperature correction, actually the impact is significantly less. The temperature impact will also impact the evaporation in the future. So here let's show you a paper by Prudhomme in PNAS 2014 from the EasyMap data, which is a large ensemble of hydrological models that has been used in combination with climate models to generate future outlooks of droughts, but also floods. But of course, we focus here a little bit on the droughts. And you see some hotspot areas that pop up very frequently, like the Mediterranean and also South America, some of South America. And they actually show that there's also a signal to noise. That's the picture on the right, and that for the red regions, you can actually say that the signal to noise is very good, and that you have a very clear indication of where things are heading. And this is 2014, and this field is moving rapidly. I mean, we've been 6 years past the study, and there's more and more have been done. For example, we now have the new CMIP6 simulations, which provide higher resolution, more data on that we can use for climate projections on drought. Here I have a paper in Earth Future from 2020 by Cook et al. And it basically shows a similar pattern. At the top, you see the winter on the Northern Hemisphere, and on the bottom, you see the summer on the Northern Hemisphere. And you see also for Arctic regions here that actually runoff in summer is going to increase, at least if you believe the models. If you go from left to right, you see more severe SSP and RCP conditions, so warmer and more impacted. So in the Arctic, you have melt, and that's most often it's melt of permafrost or snow or earlier melt of that. And then in summer, if you look at the bottom row, you see again that patch in the Mediterranean popping up like severe decreases in runoff, which will have a significant impact. This was also nicely shown by Samaniego et al. In Nature Climate Change in 2018, where they showed the changes in drought area under different warming levels, looking at 1, 1.5, 2, 2.5, and 3 decade global warming. And what you see is the area in drought on the top, where you see on the left, top left, in number A, you see what if we don't take into account changes. So you see 50% increase in that area. So that's quite a significant increase. If you do take into account that the norms and the climate is changing, then the impact is a little bit less. And you see the same for the durations that are, we get more longer, more severe droughts. And they hypothesized that actually with this climate change will also become a new norm. So the droughts that we think are heavy now will not be as heavy anymore in the future. We will just see them as a nice summer day, to put it bluntly. Other aspects, this recent paper by Livni and Badger in Nature Climate in 2020 showed also that these expected changes in droughts and climate change will not only affect the drought itself and the runoff, but also the predictability, for example, of snow droughts and winter discharge, or actually spring discharge in this case. Only in all the red spots, you actually see that we have more difficulties trying to correctly predict those snowmelt peaks. And that's also, of course, very important if you look at reservoir management and other water management issues. So that shows already quite some impact here in the Western US, for example. If we go then to the concept of flash droughts, which has been identified in 2016 by Moe and Lettemeyer and have been heavily studied since, we actually also see that those are increasing. So there's very rapid onset flash droughts that occur due to extreme meteorological conditions, and they're likely to expected to increase in the green areas over there. And you see the trend on the right for the historic period. You see a spike towards 2011, but that's I think we should just look at the general trends in that sense. But all these things and all these impacts are expected to change already from what we have now. But I only talk here about natural and human natural conditions. But coming from a country that is basically man-made, here you get a nice picture of what you can get when you land on the airport of Amsterdam. You can actually see that nothing here is man-made or natural, and everything is man-made. So if we want to study droughts in the future, we should actually take into account the human actions and the human impact. So here I show you a study we did, Yoshi Wada and myself did in 2013 when we were both doing our PhD as a side project, which was a very fun side project to do. And what we did is we actually included humans in our simulations. So on the left, the left three pictures for the US, Europe, and Southeast Asia, you see the natural conditions, the natural standardized deficit volumes. That's a measure of drought. In the center row, you see what happens when you do include humans and their water consumption, their irrigation, their households, their industry, their livestock. And you see that the brown areas are popping up, making droughts more severe for a couple of cases. And on the right, you actually see a summary of that, and you see the relative contribution of humans to the natural drought signal. So that's quite severe. And not taking that into account would actually give you a skewed image of the future. Yoshi and I continued in also still during our PhDs by doing Wanders and Wada in the Journal of Hydrology, where we actually looked at the different components. We tried to include irrigation, yes or no, reservoirs, yes or no, and looked how they will affect droughts in the 21st century. And all the blue areas show that human actions are very likely to decrease the drought impacts. And all the red areas are very likely to increase the drought impacts. This is all an ensemble of GCMs and models, but I just summarized in one picture here. And the blue areas are mostly generated by a smart reservoir management, while the red areas are often caused by increased groundwater pumping and irrigation, and thereby leading to more droughts on the long term. So human water management does impact the drought here as well. And we can see that as well if we zoom out a bit. So here I made this animation from 1900 until 2010 from the top of my head. We studied together with Giuliano de Baltasare, who is actually giving the Witherspoon lecture this year. We looked at the impacts of reservoirs on water use and dependency of people. And you can see here in this animation, I only show you here not any results on the paper, but I just show you how reservoirs impact major river systems around the world. And we start out pretty much in blue, and we end up pretty much everything red, or at least North America and Europe. And you can see that the percentage of global natural rivers is very limited at this point. And you see on the bottom, you see the number of reservoirs per continent, and at the bottom right, you see the total storage in cubic kilometers. We had this decade of engineering between 1960 and 1980, the 2 decades where we constructed a lot of those reservoirs. But that has a major impact. And not including that would actually limit your insight and knowledge of the system. Anne van Loon actually made a very nice graph on that in Nature Geoscience in 2016, where we say, like, you have climate-induced droughts, so basically only caused by climate, and you have human-induced droughts that are just there because humans are using water or affecting the hydrological system in another way. And you can have, of course, have a human-modified drought where you already have a natural drought, but you add more to that. So I wanted to actually not spend an whole historical, but I also wanted to go into the new developments, and I put it here, model developments, but new developments. And I try to highlight here that things that I find interesting that are currently happening, done mostly by early career scientists, because I think there's some very exciting stuff happening in that regard and happening in that front. I start out with a non-early career scientist, but Mark Beek has already made a nice graph, at least one I like, on how we've been developing global hydrological models through time. We started with the very first bucket model in 1969 by Maname, and then actually we developed further and further, and things become more and more complicated. And on the other hand, we have also included more and more models. So you see that the number of models is increasing. There's some crossovers, there's some change. Some models become more hybrid and can deal with more things. You have the typical on the top, the hydrological models, and then you have also more the land surface models, and you have the dynamic vegetation models at the bottom. And you can see that there's a lot has been going on, and this graph only goes until 2015, but I'm guessing until 2020 even more will be added, and more new model versions and components will be in there. One of the things I like is the approach by Martin Clark, where they actually try to have an environment where we can exchange components and interchange different modules of models, thereby looking and understanding better the impact of selecting a certain model. It's been shown that the choice of a model is not necessarily driven by the fact that you want to have the best model, but just by the fact that you can actually use it and run it and start it. And this kind of tools, as here depicted, actually give you the ability to actually change and adapt your model structure in a way that it actually is very suited for the things it should do. I want to start by in the new development section with hyper-resolution modeling. I mean, it's the term has been out there for a while, and it's been seen as a nice opportunity to provide more detail and a pathway forward if we want to further understand the global hydrological cycle and the impact of different components. And one I think is a very interesting approach, the one taken by Nate Cheney, currently at Duke, who developed HRU kind of concept on top of a core scale global circulation model. And you can see here he takes 1 pixel and then finally make a way more up to 30 meters resolution simulation of, in this case, vegetation. And then you can think, of course, that it's a nice exercise. It gives nice pictures. You can see some structure. You can clearly see some elevation impact there. But actually, what I found most compelling was when Nate showed me this comparison between the LIA simulation, so leaf area index simulation, so the vegetation leaf density, and on the bottom, the Landsat area. So the top is just model driven, given by topography and other components. And then the model resolves how the vegetation should look. And then the bottom row is actually what it is in reality. And I was quite impressed by the resemblance between the two rows. And that actually gives me confidence that this is a nice approach to take and a route to take and apply. We recently has a new paper. I think it's still in discussion, so if you want to have a read, just go for it. But where he also coupled this approach to a better stream routing network. And what you see on the left, you see the latent heat flux, and you see his original 2018 work. You see the stream, you see an uncoupled approach, and then he coupled it with a more advanced routing model, and you see more streams popping up, but you can definitely see the impact on the latent heat flux. So there's definitely an impact of including this sub-grid heterogeneity in your model simulations, not only in the hydrology, but also in the feedbacks to the atmosphere. On the right side, you see the root zone soil moisture, and then here again, you see the uncoupled simulation. On the left and on the right, you see the coupled simulation. And you can clearly see there as well that by including that connection, you actually have an impact on the root zone soil moisture and also the wetness close to the streams. And you could think, how is this related to drought? Of course. But this is very important when you think of the long duration droughts and the ability of nature to deal with those, because if vegetation is close to those streams, it is actually more resistant to those long duration droughts and might be able to survive these kind of aspects. So that's quite a very exciting development, I think. Another exciting development that I look to with great enthusiasm is like the development from ParFlow, from Reed Maxwell's group. This is the GMD 2015 figure, but ParFlow simulates at a very high resolution, simulates the continental United States, and I know that they can do more at this point, Europe as well. By solving all these equations, not like in a traditional block type kind of way that global hydrological models do it, but really solving the equations in this way, they can actually provide very nice simulations. And the simulations look nice, so that's a compelling selling picture. But also, if you look at what does it mean, and this is work by Foster et al. And ERL, and this year, published this year, it also has an impact. I mean, it's not going from 1K to 100 meters that it's just nice pictures. It also has an impact, in this case, on the evaporation. The change in evaporation between a 4 degrees warmer scenario and a baseline. I mean, they simulated a climate change experiment. But if you do that on the left side in a 100-meter simulation, you can see that especially for the evergreen needle leaf, there's a significant impact on how that translates into the future. And on the right side, you see a smaller picture, but you don't get those outliers that can be so important, and especially when you're looking at the extremes. So I think that adding resolution is, of course, first of all, a challenge, but it also might provide new information that is much needed, especially when you look at these extreme drought events that are happening in the future. This is also actually confirmed by a different study by Evelien van der Linde in Hesse in 2018, where she just looks at the impact of resolution on general circulation models. On the top left, you have the 83 kilometers at the equator Corsair model. That's a model typically used in the CMIP5 setup. For the atmospheric people among us, T159. I always have difficulties with this, so that's why I put the kilometers there as well. And on the right side, you see a finer resolution model, and that's even finer resolution at the current ongoing CMIP6 simulations that we have. And you see the drought in months. So you basically see the more red, the more drought. And what she shows is that by increasing resolution, you actually get more drought with the same model. And whether or not that's true, I mean, in this case, it can't be validated, but that will definitely have impact when you look at climate projections and the IPCC reports. If we go to finer resolutions, we might actually be able to detangle more droughts that are happening in the future than we currently estimate. So our current estimates might be actually on the conservative side. Then models matter as well. We often use a model, a hydrological model, but here I took a graph from Talix and staff from GRL 2014. They looked at the autocorrelation of certain models, and it doesn't really matter which variable here, but what you see is that the autocorrelation drops off for some models very rapidly. So the memory in such a model is only 10 weeks, something like that, while other models have a tendency to take way longer to lose that memory. And that's again important when you try to simulate processes, long duration, large extent processes like droughts that typically last for longer times. Because if the model forgets about its earlier state faster, then the recovery is faster as well. While if the model has the tendency to slowly recover, that has a significant impact. And that's actually also shown by Lieke Melse in 2018, where she compared models, forcing them with different GCMs and see how much they agree or mostly disagree. And this is done for the US. And you can see that there's quite some disagreement between models. And therefore, it really matters what kind of model you take, if you take an ensemble or if you take a selection. Her paper actually goes into all the details of different GCM combinations, models combinations, and so on. But I thought this shows you just how important it can be to be aware of these artifacts. Then she also dived into, in a later paper in the WR in 2019, also in the impact of the parameterization. And what you see that not only the models do matter, but also the parameters of the model do matter. So it's not just taking the one model. So I have VIC here, the variable infiltration capacity model. And she actually looked at different climate zones going up into this graph. And you see that the sensitivity of the parameters for drought predictions, she actually focuses on drought, is first of all relative per climate. And second of all, you see quite that only some parameters do matter for drought. And I think that's an interesting finding when, if you calibrate models, what is your objective function and what do you try them to mimic or to reflect? And then I think I want to move away a bit from the model development and look a little bit of new developments in multidisciplinary science, because I think a lot of the exciting developments are done in that field, where we combine our knowledge as an hydrology community with the atmospheric community, the vegetation community, or other branches at AGU. And I think that sometimes we can really push both our fields forward. And I've been really enjoying those collaborations as well. And I think that's also why I want to advocate for them here. So one of them is where we collaborated with Karin van der Wiel from the KNMI in a 2019 GRL paper. In the atmospheric community, they have these large ensembles of where climate models are used to generate, in this case, 2,000 years of weather events. And the advantage is that Karin did this in such a way that actually the atmosphere was coupled to their land, to their ocean. So it's a system that is capable of reproducing physically extreme things. And by using a dynamical model, we don't have to rely on the statistics. So the model can theoretically go everywhere as long as the patterns are there. We looked at the present day in a 2-degree warming climate, so that's on the bottom left, just to compare the differences. And then we run it through our global hydrological model, PCR Glob, just to generate global discharges around the world and look at the extremes. And without going into all the figures in the paper, I think you can pick those up yourself and read it. I want to show you the impact of using 2,000 years and not 100 years. So the simulation starts by adding 5 years at a time. And this is for the River Rhine, which is a Dutch river. But yeah, since I live there, that gives me some reference. And I color-coded all the red lines to be the driest of them all, and the blue lines to be the most wet of them all. And then the yellow is a little bit in between. First of all, you see that some of the red lines start out low and go high and go low, and they go over the place. Some of the blue lines do the same. So it's not like they always stick in their own zone. So you can't say, oh, this year starts out dry and it's going to be a dry year after all. And second of all, if we start the animation again, what fascinates me is that even after like 1,000 years that we already had. Adding new ensemble members will still give us events that we have not observed before or simulated before in this case. And also, if you go and look into the distributions of those events, they don't always tend to follow the generalized extreme value distributions. So actually looking at those extreme tails can give us a lot of information. So now you can actually see, if you look at the high end specifically, then you can actually see that some of the lines pop up now, like extreme events that have not been observed before. And of course, this experiment is not there with the aim to look at the 1 in 2,000 year event, because the chance of that happening are very slim. But it does give us the ability to generate 20 1 in 100 year events and look what kind of patterns they might have in common, and what kind of predictor they might have, and how we can prepare better for those. And I think this is very exciting exciting new thing to do by combining atmospheric science with our hydrology knowledge and looking and understanding together. Another interesting thing is linking hydrology again to meteorology, and this is a paper by Julio Herrera Estrada and Noah Diefenbach in WR this year, actually recently published, I think a couple of months ago. And they look at landfalling droughts. And when I first read it, I was like, landfalling droughts? But it's basically droughts that can be predicted by oceanic anomalies between precipitation minus evaporation. And they actually find that most of the severe droughts, or a lot of the severe droughts, are actually coming from the ocean. The exact mechanism, they don't go into detail on that, like what could be the predictive causes and so on. And we've long known that ENSO and El Nino have an impact on drought frequency, but this connection with the ocean is quite interesting, and they track droughts through the atmosphere and over land. And I think that this by looking at these other sources of predictability is quite an interesting way. You can also see that on the right side, also on the left side, you see the frequency of the landfalling drought, so how many you have per year, and you can, as you can expect, on the west coast, as you have more of those than you have in the interior of some of the countries, and also the extent, so the size of those droughts, and they actually tend to be quite big. Julio already showed in an earlier paper that you can actually predict droughts by tracking them over land. So, and I think this is a nice add-on, something that needs further study, but is very interesting first approach here, I guess. Then some other things is linking hydrology to vegetation. Recently, we've been coupling our hydrological model to a dynamic vegetation model and showing what the impact is of the drought with and without these coupling processes for the dynamic vegetation model. And you can actually see that not only does it improve the simulations, but it also shows impacts on the near infrared and the carbon production or the carbon fragmentation in simulation. So by linking our hydrology to vegetation dynamic models that might have a different simulation of the unsaturated zone and certainly the groundwater, actually causes a different result in terms of carbon uptake and other fluxes toward the atmosphere. And linking our fields there, I think, is very exciting, and especially also if you look at the drought recovery phase, where a lot of the hydrological models will just have vegetation that magically evaporates water again as soon as it has water, because our vegetation is often not dynamic. Well, in this case, is by coupling the two, we can actually incorporate processes like leaf shedding and so on. Then another thing we've been developing in Utrecht is linking hydrology to water temperature. And of course, water temperature is a component of hydrology, but it's more and more used by other disciplines. So here I have the annual water temperature change in the decades over the historic period. But we published this paper as we wanted to see if we can do this. But most of the interest actually comes from different communities, like people that study biodiversity around the world. So we teamed up with Valerio Barbarossa in Nijmegen, also in the Netherlands. This is a work in progress, but it's actually submitted actually. But they look at the impact of water temperature change and discharge changes on fish species. And they used around 7,000 fish species around the world. So you see the world here again. And where everything is yellow, the impact of climate change of, in this case, 3.2 degrees warming is not that bad or is low. I wouldn't say that not that bad, but maybe low. And where the impact is blue, it's very high. And they actually have lab experiments where they professionally kill fish by raising temperatures for the fish species and seeing when they die. And that gives them their comfortable niche. We know where those fish swim in which rivers. So we actually can see if this river system warms up more than certain amount of degrees Celsius, this fish will have no existence here anymore. And that's very exciting work. And we've also been teaming up with other groups around the world to look at these kind of things, and invertebrates, but also fish species in this case. So very exciting. If you look at the summary of that work by Valerio, you can actually see that if fish get the opportunity to have dispersal, so they can swim to a different river, then they are actually a little bit better off. But still, if you look at the 3.2 degrees warming scenario, you go from 40% species loss to something like 20% species loss. And 20% species loss around the world for all fish species is probably not a good thing. But it is very exciting to collaborate on these kind of things, although the reports or the findings might not always be very happy and positive. And that especially is true for the next topic that we've been studying here in Utrecht together with Sophie de Bruin and Janus Hoch, two postdocs. We actually look at the impact of hydroclimatic change and conflicts. And this is a paper by Magnetal in Nature in 2019, and actually they interviewed a lot of experts in this topic, and they said, what do you think happens with conflicts to date and how are they related to climate? Most of them agreed that currently climate is not that big an impact on conflicts, but they expect moderate increase to substantial increase when we go to 2 degrees or 4 degrees global warming. So that indicates that, and I think that you can also see that in a lot of research programs around the world, that climate change is will affect conflicts in the future, at least expected to do so. So we try to simulate this now for Africa and try to get a model to actually link climate to conflicts and also other socio-economic factors. This is still work in progress, but exciting to look at these other avenues. Then I want to go and end this by going to a little bit more personal message. I mean, this was all very science, and I think there's a lot of exciting things, but I think as scientists, we also have the ability, the duty to communicate our science, and especially when you talk about hydroclimatic change, droughts, floods, climate change. Do it on Twitter or in media, or even give school lectures to kids or something like that. I really enjoy that last category. Kids are very open in their questions, and they're also very honest in their opinions. And I think it is our duty, even though it's sometimes difficult and you might have haters around the world, to communicate that your findings in a nice way and try to say what you have and how we can prevent some of the impacts. So in summary, drought has many different aspects, many different phases, many different ideas, and I think there's a lot of exciting new developments happening in human interaction with water, the model development, so we better understand how our models affect the drought impacts, the link from droughts to impacts actually, so linking the physical phenomena to on-the-ground impacts that bother people like crop loss or conflicts, and we have to communicate our findings. And I want to end on a very personal note, and I think we should also enjoy our science. At least that's something I did. I think I have an awesome job here on the left side, giving lectures in the field, repairing a meteorological station in Nepal at 4,000 meters, reading a precipitation bucket, and at the right side, you wouldn't say so, but that's AGU full meeting last year. And I think, and I do that with other scientists who can't be on the picture because of European law. I'm not allowed to put them on there without their consent, but I have amazing friends around the world that join me in some of these adventures, and I think I'm very grateful that I can have this job and do it and give this lecture now to you. So with that, I would like to thank you all, and I'm happy to take any questions.
Thank you, Niko. Thank you for communicating your science in a wonderful way and still having fun with what you do. That is great. It's been part of my life as well. We're open for questions, so please, thank you. Let's give a round of applause virtually to Niko. Thank you, and please type your questions into the question box. We have a large number of you out there, so looking forward to hearing from you. Niko, I have one question, maybe to kick things off, which I found interesting. So I found all the talk very interesting, but when you were talking about linking hydrology to other disciplines and coupling with vegetation modeling, so bringing the vegetation modeling community in, the ecology community, if you will, with the hydrology community, and you said, so we treat leaf area index differently than a vegetation modeler would. There may have a different algorithm. If you're going to couple those two together as you did, how do you decide who wins, if you will? Which community wins in, say, how I treat soil moisture or how I treat leaf area? And because are you making a qualitative judgment that if it's green, then the vegetation modelers win?
So yeah, first of all, we in this case we actually validated with remote sensing data that was available, so we can actually look how the simulations look from a remote sensing point of view, and as you would say, an independent observation, and which community wins in that case. It's a little bit more difficult, of course, for soil moisture because we have remotely sensed soil moisture, but that's only for the top 5 centimeters, and the observations that are observations are only have a very limited spatial representativeness. So that's a little bit more tricky in terms of groundwater. Often or at least the model group we collaborated with didn't have any groundwater interaction there. So that's something that we kind of win on. But I think you try to see with independent validation as much as possible, what is the best representation of the process. But then still, after coupling, things could get messed up, of course, because coupling models doesn't always mean they're going to be better. But yeah, that's still up to that validation data set to decide on how we can improve those couplings.
Okay, thank you. Very good. We have a question from, and I do apologize to begin with, to my Dutch colleague, Wouter Berghuis. With the current generation of models that can incorporate so much detail, how do we quantify and communicate what part of the model outcome is robustly supported by data and theory, and what part is still uncertain?
Yeah, I think that's one of the challenges, because if you go to these like 1K or sub 1K grid cells, it's very difficult to be able to validate in every point and be able to say I have full trust in all of it, especially if you start calibrating. And in that sense, I'm always in favor to not calibrate. It sounds a bit, but get the processes right. I mean, if we have the processes right and we get from an independent observational source, we'll be able to tell, this mimics reality. Then you can have some faith in that you can also do the same for other locations that you might not have any observations on. So, for example, the graphs I showed from Nate Cheney, his LAI simulations. There's no calibration in that process. So if you simulate LAI and you get a picture that is representative of a satellite image, then I think you can have confidence in that the modeling setup also performs well in other regions. But you always have to be aware of the caveats of our model. So for our global model, I know where I would trust and where I would trust it less, given our extensive validation we've done over the past. And I think that's also for the scientists to be able to capture that or give that information also to the user, whether that's a media journalist or whether that's a fellow scientist. I think you should be able to also communicate your uncertainties there, where you trust the model and where you have little trust. I think that's that will be my answer, I guess.
Okay, thank you. Very good. Niko, this question comes from Todd Caldwell. Awesome to see these hyper-resolution models, but in your opinion, what data are still missing? What forms of data are missing to validate some of these models? In your opinion, what are the biggest ones? Yeah,
I think soil moisture is one that is really difficult, and groundwater. Those two water sources we don't really see. The spatial representativeness of the measurements that we have is limited, and also the point measurements is sparse. So if you look at precipitation, there are way more gauges on that. Discharge gives a kind of an integrated measure over catchment. Of course, more discharge stations will be better, but For soil moisture and groundwater, it's very difficult because the spatial representativeness is limited and we don't have that many points to validate on. I think we both, the United States and the Netherlands, are fortunate in terms of groundwater measurements. But if you go across the rest of the world, it's a little bit more challenging. And for soil moisture, I think, yeah, that's challenging around the world. And but with the outcome of remotely sensed soil moisture, I think we have gained some addition. For GRACE, for example, for groundwater measurements, add something, but there's still quite a coarse spatial resolution that definitely doesn't help to validate a model at 30 meters.
Okay, thank you. Our next question comes from Carol Dahlen, and it's, hi Niko, congrats and thanks for the talk. About human impact on drought. Is that right that dams and reservoir intervention in your Journal of Hydrology paper leads to less drought? And if so, what about downstream water flow reduction? How is the drought defined in that case?
Yeah, so in general, on average, it does, and that's because, but that's also assuming that you do the management properly. So of course, you get additional evaporative losses, but by changing the flow distribution around the year, you can actually gain more than you lose in a sense. I must admit that for that paper, it's still the evaluation is still on a basin level or slightly closer than the downstream losses, which there are, and they're not negligible. They will be compensated by upstream gains, I would say. So yeah, I think that's also assuming that people do their management properly. And I think we've seen some nice, no, not nice, but we have seen some real cases in where water management in reservoirs is challenging, especially with sentiments running high after droughts or before droughts. So I think that's still that's something that yeah, is a limitation in that study. Okay.
Okay, and Carol sends back a thank you. So thank you, Carol. The next question is Suzanne Groot. Can you predict in which location or circumstances a high resolution model would perform better than a low resolution model in predicting drought? What are the criteria there?
I would think that typically in areas with high heterogeneity, you would probably have a more advantage of a high resolution model. We also saw that from Foster's work at all. You saw that like the changes in evaporation, if you look at a climate change scenario, you see some very impressive evaporative changes. And that's it's often, at least also combining it with the things we see in the Cheney coupled work. There you can kind of hypothesize that it's either close to streams or very far from streams. So that kind of slow or that high heterogeneity within it in the landscape would actually also make different processes dominant at different locations. So I think if you have that high heterogeneity, so mountainous regions, let's think about the Rockies or something, yeah, there I think you would gain a lot. The difficulty there, of course, is the parameterization, which would suffer from this high heterogeneity and the lack of input data we might have there. So that's a downside. But yeah, I think that's where we, in the end, we would gain most. Also, if you look at precipitation gradients, but we don't have the data on that, but the precipitation gradients and runoff process on very steep slopes that cannot be captured by the large scale models, but can only be captured if you do some things at a very high spatial resolution.
Okay, thank you. Next question comes from just down the hall, I think from Mark Birkins. What's the most, and I may have to read this twice to make sure, because there's a few uncertainties in this. What is the most uncertain factor that makes future projections of drought intensity uncertain?
That's a couple of uncertainties. Yeah, I think it's still our hydrological modeling chain. So I think the GCMs or the forcing data is there, or at least they show a larger consistency than the representation we have in our hydrological models at the moment. Also looking at some of the papers, for example, by Prudhomme and Lieke Mels's paper as well, they also confirm this. And I think how we incorporate the processes, on what resolution, what detail, and that all matters towards how the future projections look. We've recently done a project with UFZ, the EDGE project, and we had 4 hydrological models, and already the differences were noticeable, while the GCM data was more or less in the similar direction. So I think as a hydrological community, that's still a challenge. I'm not saying we have to always use one model that's the best model, or always take an ensemble, but be aware of the different results that you will get with the different models, especially when you want to draw very large conclusions. For example, is human water use and human water feedbacks, are they included in your model? That does make a difference. And if you have a natural system, that actually limits us, of course, then in a sense, the climate projections you can do, or at least the confidence you can have to say this is what's going to happen.
Okay, thanks. Perhaps suggesting another round of model intercomparison is needed.
Yeah, there are already some. I know.
Yeah, but it's serious. Yes. All right. So good question here. Thank you, Mark. A good question from Sally Rangecroft, and this is a tough one. How do you best overcome the challenges of communicating uncertainties related to your modeling to the general public?
Yeah, that's a very tough one, because what I typically try to do is, or what I try to show is like what the uncertainty looks like. And if you say, for example, a drought is, or at least the chance of drought double, if you want to say that, then I often say within a time range of between 30 and 50 years from now. Not saying it's going to be 40 years from now, but giving a indication of the range. And I think most people can actually, yeah, when you give such a lecture and they understand that there's uncertainty on these things. And I think it's also more convincing message if you actually give them the full message, rather than just say within 40 years drought chances are going to be doubled. So I think by including that and also showing them the graphs and the uncertainties, I think that helps. For some things we can be more certain than for others, and we shouldn't make any comments on things we don't know for sure. But I think by showing it, and also children, I mean, they understand how you roll a dice, for example, how it can, the outcome is never certain, but you have an average way it's going to look like. The average will be 3.5, but it can be a 6 one time and a 1 the other time. So, and they understand that as well. So, yeah.
Okay, thank you. I think that would make a great town hall or panel discussion at the 2021 AGU meeting, to talk about experiences of communicating these uncertainties. All right, our last question comes from Remco Ouwenhout, excuse me, and Niko, which is who won the bike climb at the AGU 2019 meeting? Apparently, it wasn't Remco.
No, he didn't join, so that's a pity. You know, I always try to get out with some of my collaborators to go the day before AGU. So I will not name any names, but it was a nice. It's always a very nice ride there. We can exchange ideas and have some fun. I think that's the most important thing that we can have, and the friends that you get from those science and AGU full meeting gatherings. So next time Remco can join if he wants to.
Okay, next time I'll join. It's in New Orleans, so it won't be much of a climb. Very good. All right. Well, thank you. Very good. Remco replied, diplomatic answer. All right. So thank you, Niko. From the audience, if you will, let's give Niko a rousing round of applause. Wonderful talk, Niko. Thank you very much. Much appreciated and stimulating. And we look forward to seeing you virtually at the AGU meeting. And yep. Thank you.
Thanks, Scott. Thanks.
Very good. And Niko, if you can just pop to your next slide, I've got a couple things to say. I just want to thank everyone. So this concludes our 3-part early career awardee lectures in November. I think they're really successful. I think we can do this again each year. I hope so. And I hope I'd love to hear feedback from all of you who have been listening over these last couple of Friday mornings. Thanks to all the folks who nominated our early career awardees and all of the early career awardees. We had quite a large pool this year, so thank you very much, and all the letter writers. I also want to thank the Early Career Award Committee which is chaired by, this year was chaired by Ellen Wall, and had members Jim McNamara, Monica Riva, Andrew Western, and Fucain Tian. So thank you very much. And also, I just want to thank Greg Bindner from the AGU, who's been in the background here. None of you have heard him too much. He's been making sure that this webinar moves smoothly through. So very much appreciated to him. And I think we've had really ease and good work through this. So thank you, Greg, and all AGU. Niko, next slide, if you would. There we go. Okay, a couple of things just to remind everybody what's going on. I know it's a confusing meeting and it's a challenging meeting. First off, before we get into what's happening at the meeting, I sent out a note late yesterday because I got heads up from AGU that for those of you who are worried about uploading your presentation, which was due today or is due today, they're giving everyone a grace period until Monday, this coming Monday. And I'm not going to say what time it is because I can't remember the time, but it's in your email. I sent it out. It's also on the Hydrology website. So you do have a little bit of time over the weekend. They realized people were getting a bit panicked, and I'm sure many of you may be getting a bit panicked. So calm down, everything will be fine. A couple of the important things for the meeting. So first off, let's go to we're trying to keep our events that we do when we're in person kind of on the same time frames so that we keep some traditions and we don't confuse you too much. Still will be confusing, but we'll do the best we can. So as normal, our Langbein lecture will be on Tuesday, and that's December 8th, and that is from 13 to 1500 Eastern Standard Time, so kind of afternoon Eastern Time, early evening European time. And we will also do part of our awards during that Langbein lecture. Because we don't have quite as much time as we normally do, we're going to split the awards. Our Witherspoon lecture, the other lecture, is also on Thursday. It normally is on Thursday, same time, and we will. That's where we'll celebrate actually our early career awardees during the Witherspoon lecture. The lectures will be recorded, but there'll be live question and answers after each of the lectures. The hydrology section business meeting is on its normal date and time, Tuesday, December 8th, roughly dinner time, East Coast time. So it's okay to bring your beverage to the business meeting. That lasts about an hour. I do encourage all of you to tune into that. Basically, it's an update of what the section is doing, what the section has done over the past year, and where we're going for the next year. You'll get to introduce, we'll get to see the new section officers, et cetera, and hear from Kawasi, from Water Resources Research, from our student section, and from our OSPA award winners. All right, so those are the key things as far as our normal things. Town halls, 2 town halls I want to call your attention to. One is early in the AGU meeting, December 1st, and that's a town hall put on by our student section to talk about what the section is doing and can do and hear from you about justice, equity, diversity, and inclusion. And then the next town hall is December 7th, which is Monday in the afternoon. And that's going to be chaired by myself and our new Hydrologic Sciences Frontiers in Hydrology meeting program committee for the meeting that will be held in 2022 joint with Kawasi. So we'll give you some updates there, and then we want to get some community input back on those. Let's see, what other things do I need to tell you? One last thing, which is keep an eye out. We're working on having during the what would normally be the cocktail hour at the fall meeting, we're hoping to have kind of meet and greets for the various section volunteer groups. So we'll have a WRR meet and greet one evening, meet and greet your technical committees, which help organize the sessions, our fall meeting program committee, the new executive committee, things like that. So I'm hoping to run those pretty much starting after Tuesday, the 8th of the business meeting. So from the 9th on to whenever the meeting ends, which I think is sometime, the meeting seems to end in about 2032, I think is when it feels like. No, it's December 17th. All right, I think that's all I have to say. If there's any other questions, I'm not seeing any. We're coming right up on the hour. Again, thank you to Niko, to Simone, and to Veronica for outstanding lectures this year. And we look forward to seeing all of you at the AGU meeting virtually. So thank you all, and stay safe and stay well.